Welcome to our deep dive into the Transformer Encoder layer in PyTorch. In this tutorial, we're going to build upon what we learned about scale-product attention and explore the complete encoder layer architecture. We'll understand how self-attention combines with feed-forward networks, master the importance of layer normalization positioning, and learn how all the parameters affect model behavior. By the end, you'll be ready to build practical sequence processing models using TransformerEncoderLayer. Let's start by understanding the TransformerEncoderLayer architecture. While our previous video focused on scale-product attention, the TransformerEncoderLayer is a complete building block that combines multiple components. It includes multi-head self-attention, which uses scale-product attention internally, a feed-forward network, layer normalization, and residual connections. Looking at this architecture diagram, we can see how these components connect together to form the complete encoder layer. First, let me set up our environment with all the necessary imports. We'll need PyTorch and its neural network modules, along with some visualization libraries to help us understand what's happening inside the layers. Great, we're running PyTorch version 2.5.1. Everything is set up and ready to go. Now let's dive into the simplest possible example of a transformer encoder layer to understand its basic operation. Here's our simplest transformer encoder layer example. We're creating an encoder layer with a model dimension of 512 and 8 attention heads. The model dimension determines the size of our feature vectors, while the number of heads allows the model to attend to information from different representation subspaces. Notice that we're creating input with shape sequence length, batch size, dmodel. This is PyTorch's traditional format. After passing our input through the encoder layer, we can verify that the output shape matches the input shape, which is a key characteristic of the transformer encoder layer. It maintains the input dimensions throughout. Perfect. As we can see, the input shape is 10 by 2 by 512, representing 10 time steps, 2 samples in our batch, and 512 features. The output maintains exactly the same shape. This dimension preservation is crucial because it allows us to stack multiple encoder layers easily. Let me show you a comprehensive table of all the parameters available in TransformerEncoderLayer. Each parameter has a specific purpose and effect on the model's behavior. The dmodel and nhead parameters are required and determine the basic architecture. The dim feed-forward parameter controls the hidden layer size in the feed-forward network, typically set to 4 times dmodel. Dropout helps with regularization, while activation determines the non-linearity used. The batch-first parameter is particularly important as it changes the expected input format, and norm first determines whether we use pre-layer norm or post-layer norm architecture. Let's explore the batch-first parameter in detail. PyTorch traditionally uses sequence length, batch size, features format, but many practitioners prefer batch size, sequence length, features because it's more intuitive. Here we're comparing the two input formats. With batch first equals false, we use the traditional format where sequence length comes first. This means 20 time steps, then 4 samples, then 256 features. With batch first equals true, we switch to the more intuitive format where batch size comes first. So we have 4 samples, 20 time steps, 256 features. Both produce outputs that maintain their respective input shapes. As we can see, the sequence-first format has shape 20 by 4 by 256, while the batch-first format has shape 4 by 20 by 256. Most modern implementations prefer batch first because it aligns better with how we typically think about batch data. Now let's examine the feed-forward network structure. The FFN is a crucial component that processes each position independently after the attention mechanism has aggregated information. Looking at this diagram, we can see how the feed-forward network expands the dimension, applies an activation, then projects back to the model dimension. Let's explore how the dim feed-forward parameter affects the model. We'll test different feed-forward dimensions and see how they impact the total number of parameters. The feed-forward dimension determines the size of the hidden layer in the feed-forward network. A larger dimension gives the model more capacity, but also increases parameters and computation. Notice how the parameter count grows significantly with larger feed-forward dimensions. Starting from 527,000 parameters with dim feed-forward equals 512, we go up to over 2.3 million parameters with dim feed-forward equals 4096. The typical choice is to use 4 times the model dimension, which in our case would be 1024. One of the most important architectural decisions is the position of layer normalization, controlled by the norm first parameter. This diagram shows the difference between pre-layer norm and post-layer norm architectures. Pre-layer norm, where normalization happens before the sub-layers, tends to be more stable for training deep networks. Let's compare pre-layer norm versus post-layer norm behavior in practice. Post-layer norm is the original transformer design where normalization happens after the residual connection. Pre-layer norm, on the other hand, normalizes before the sub-layer, which has become more popular for its training stability, especially in deep networks. Looking at the output statistics, we can see that post-layer norm produces outputs with mean very close to 0 and standard deviation very close to 1, thanks to the normalization at the end. Pre-layer norm has slightly different statistics, with a small non-zero mean and standard deviations slightly above 1. The mean absolute difference between the two outputs is about 0.34, showing they produce meaningfully different results. Now let's analyze the gradient flow differences between pre-layer norm and post-layer norm architectures. This will help us understand why pre-layer norm tends to be more stable for training. Looking at these gradient flow visualizations, we can see the gradient magnitudes for different layer components. The left chart shows the raw gradient norms, comparing post-layer norm in red versus pre-layer norm in blue. The right chart shows the gradient ratio, where values closer to 1 indicate more stable gradients. Pre-layer norm generally provides more consistent gradient flow, which is why it's often preferred for deep networks. The activation function in the feed-forward network significantly affects the model's expressiveness. Let's explore different options. Here we're testing 3 different activation functions. RayLU is the classic choice that zeroes out negative values. GELU, or Gaussian Error Linear Unit, provides a smoother alternative that's become popular in transformers. We're also testing a custom swish activation implemented as x times sigmoid of x. All 3 work correctly with the encoder layer and produce valid outputs with similar standard deviations. All activation functions are working correctly. Each produces an output standard deviation very close to 1, showing that the layer normalization is maintaining stable statistics regardless of the activation choice. The outputs are different though, which we verify to ensure each activation is actually being applied. Let's visualize how these different activation functions behave to better understand their characteristics. Looking at these visualizations, we can see clear differences. RayLU simply clips negative values to 0, creating a sharp corner at the origin. GELU provides a smooth approximation to RayLU with a gentle curve. Swish, also known as CLU, allows small negative values to pass through, which can sometimes help with gradient flow. GELU has become the standard choice for many transformer models due to its smooth properties. Dropout is an important regularization technique applied in 2 places within the encoder layer, after the attention mechanism and after the first linear layer in the feed-forward network. Let's test how dropout behaves in training versus evaluation modes. We're creating an encoder with 50% dropout, which is quite high but useful for demonstration. In training mode, dropout randomly zeroes out activations, so running the same input multiple times produces different outputs. In evaluation mode, dropout is disabled, making the model deterministic. Perfect. We can see that in training mode, we get a variance of about 0.18, confirming that dropout is causing variation in the outputs. In eval mode, the variance is essentially 0 because the model becomes deterministic. This is exactly the behavior we expect. Dropout helps prevent overfitting during training, but is turned off during inference. TransformerEncoderLayer supports 2 important types of masks. The source mask controls which positions can attend to each other, like a causal mask for autoregressive modeling. The source key padding mask marks padding tokens that should be ignored during attention. Let's demonstrate both masking capabilities. First, we'll run the encoder with no mask to get a baseline. Then we'll apply a causal mask, which only allows each position to attend to previous positions, essential for autoregressive tasks. Finally, we'll use a key padding mask to mark the last 3 positions as padding, which the model should ignore. We can see clear differences in the outputs. The causal mask changes the output by about 0.12 on average, while the padding mask changes it by about 0.07. These masks are working correctly, producing different outputs because they change which positions can attend to each other. It's important to note that with a padding mask, the entire sequence is affected due to attention redistribution, not just the padded positions. Now let's build a practical sequence model by combining TransformerEncoderLayer with other components. Here's a complete sequence classifier using TransformerEncoderLayer. We start with an embedding layer to convert token IDs to vectors, add positional encoding so the model knows the order of tokens, then stack multiple transformer encoder layers using the transformer encoder wrapper. After processing through the transformer, we use global average pooling to aggregate the sequence into a single vector, then pass it through a linear classifier. The model handles padding masks properly and maintains batch-first format throughout. This is a practical architecture you could use for text classification, sequence labeling, or other NLP tasks. Excellent! Our complete model is working perfectly. We have a vocabulary size of 1000, model dimension of 256, 8 attention heads, and 3 stacked encoder layers, outputting to 5 classes. The input shape is batch size 4 by sequence length 20, and the output is batch size 4 by 5 classes. This demonstrates how TransformerEncoderLayer fits into a complete model architecture. For our advanced section, let's examine the internal components of TransformerEncoderLayer to understand what's happening under the hood. Let's inspect all the components inside a TransformerEncoderLayer. We can see it contains a multi-head attention module for self-attention, 2 linear layers for the feed-forward network, 2 layer norm modules, and several dropout layers. Looking at the parameter breakdown, most parameters are in the attention mechanism and feed-forward network. The attention and projection weight combines the query, key, and value projections, which is why it has shape 768 by 256, 3 times the model dimension. For computational cost, attention has quadratic complexity with sequence length, while the feed-forward network has linear complexity, but typically dominates the flops due to the dimension expansion. We can see the total parameter count is about 790,000 for this configuration. The attention mechanism accounts for about 263,000 parameters, and each linear layer in the feed-forward network has a similar count. For a sequence length of 100 and batch size of 32, the attention requires about 82 million flops, while the feed-forward network needs over 1.6 billion flops. This shows why the feed-forward network often dominates computation despite attention's quadratic complexity. Let me summarize the best practices for using TransformerEncoderLayer. Use pre-layer norm for deeper networks. Ensure your model dimension is divisible by the number of heads. Prefer batch-first format for consistency. Consider GELU activation over RayLU. Start with 10% dropout and adjust based on overfitting. Use appropriate masks for your task. Stack layers efficiently with Transformer Encoder, and remember that residual connections are crucial for gradient flow. Finally, let's create an optimized TransformerEncoderLayer configuration that follows all the best practices we've learned. We'll use pre-layer norm for stability, GELU activation for better performance, batch-first format for modern conventions, and a standard 4:1 feed-forward ratio. This configuration is production-ready and incorporates all the lessons from our exploration. Perfect! Our optimized configuration is working flawlessly. We're using pre-layer norm architecture for stability, GELU activation which often outperforms RayLU, batch-first format for intuitive data handling, the standard 4:1 feed-forward ratio, and appropriate dropout of 0.1. The output statistics look healthy with mean near 0 and standard deviation close to 1. This encoder layer is ready for production use in your transformer models.